Okay, this is chapter 13.1 for Math 1325. So we changed the course number recently. 25. Alright. So we are moving on to a different part of business calculus content, and it's called antiderivative, or for the indefinite integrals. So basically, since the beginning of the semester until now, we are taking the derivative, but now we're doing the opposites. So they say differential calculus focus on the problem finding the rate of change. So we have been trying to find the rate of change this whole semester so far of one quantity with respect to another. In this chapter, we begin the study of the other branch of calculus known as the integral calculus. So we're starting integral calculus. Here we are interested in precisely the opposite problem. If we know the rate of change of one quantity with respect to the other, can we find a relationship between the two quantities? The principal tool used in the study of integral calculus is called antiderivative of a functions. And we develop rules and anti-differentiations or integrations as the process of finding the antiderivative is called. We also show that a link is established between differential and integral calculus via fundamental theorem of calculus. So we will talk about fundamental theorem of calculus, and the anti-differentiations or integrations is the process of finding antiderivative. So we will be focused on that the rest of the semester. So we started with the indefinite integral. The process of finding all antiderivative of a function is called anti-differentiations or integrations. And we use the integral signs to represent that. So if we're taking integral of a function dx, so a lot of time people forget this part, means finding an antiderivative of the function. So the last exam and chapter 13 will be focusing on that. So let's get started, and we will upload this document to D2L. Antiderivative, or the opposite of derivative. If we say this capital letter F is an antiderivative of the functions of an integral if f prime of x equal to f of x for all the x in that integral. So thinking about the process of taking the derivative, so if we found the derivative of these few functions, when you take the derivative of x, you get what? Just 1, right? So the x is gone, the coefficient stay, right? And then the second function, they have x plus 2. When you take g prime of x, it's still going to be 1, right? And for this guy, 1 again, because the 2 doesn't turn into 0, right? And the last one, we still get 1. So here is the issue. If you are given the slope of this, and you need to come back to the original one functions, we only figure out the x part, right? But we lost the information for the content parts, constant parts, the number parts. So because of that, we are going to call all these functions as a family of antiderivative of f of x. So if you look at the graph here, these are some of the functions. We can group them as a family of antiderivative of the function. So let's write that down. So therefore, f, g, h, and A are all antiderivative of f of x equal to 1. And all these functions f, g, h, and a are a family of antiderivative of f of x. So they're kind of related even though the original function don't equal to each other, but because when you take the derivative, the constant, the number part is gone, so they belong to the same family of antiderivative. Okay, let's look at the next page. So the next page, we have another family to introduce to you. Sorry, those highlights bleed out to the second page. The first theorem say let G be an antiderivative of a function of f in an integral I, then every antiderivative f of f on I must be the form of f of x equal to g of x plus c, where c is the constant. So basically, it say when you take the antiderivative, you add back like a constant at the end c to represent whatever number that we lost in the process. So looking at the parabola family here, all of these functions, when you take the derivative, is going to equal to 2x. And all the number are lost in the process, so they want you to add a c at the back to represent the constant. So they say the graph show a family of antiderivative for f of x equal to 2x. So what they're going to do is they say the antiderivative of the functions is going to be integral f of x, don't forget the dx at the end. So over here what we have is we have integral of 2x dx. To reverse the process, we will get this become x squared, and then we need to add a constant at the end. So this is one of the basic steps for doing antiderivative, which is the opposite step what we have been doing the whole semester. Alright, so hopefully that makes sense. And the next part, we are going to go with the first rule. The first rule is the indefinite integrals of a constant. So if you're taking the derivative, antiderivative or integral of a constant, so you will add an x back plus a c to represent the number that we lost, right? So over here, we started with 2, we go back with the x, add a c, and that's my answer for the integral, right? Which is the opposite of taking the derivative. You can check for the first questions, because if my function, so this is my function, right? If my function is 2x plus a number, then when I take the derivative of that, it would be just 2, right? So that seems to match. If we started with that, to go opposite, we got this. Alright, so that's one, and later on we're not going to check, because like if we keep checking, it's going to take like a really long time. So hopefully after a while you get used to the process. Okay, so b, even though it looked kind of weird, but pi is just a number, right? Taking a square is just a number, right? So it's taking integral of a regular number. So again, we started with pi square, and then we need to add back an x, and then we add a constant, right? So that's all you do with the taking an integral of a constant. Okay. Second rule, the indefinite integral of a constant multiplied to a function. So I would have this blank document on D2L. If you don't have a printer, you may want to pause the screen and write this down if you can. So apparently I'm missing one rule here. So that was rule number 3. So I messed up. So this is rule number 3. The rule number 2 is the power rule. So the power rule say if you're taking an integral of x raised to n power dx, then it would be move these exponents down 1 over n plus 1, and then on top you will have x n plus 1. Don't forget to add a c at the end. So this is the power rule. Somehow I forgot to put it there. Okay, so that rule number 2. Rule number 3 say if you have a number multiplied to a function, you should pull out the number, the coefficient first. So let me smudge just a little bit. Okay, like that, and then you take the derivative of the function. That's it. Alright, so let's try some of the questions here. I'm going to add, this is 5a and b. Let's add number 4 here. I want to take an integral of x cubed dx. Alright, separate this. Sorry, it's kind of crammed it together. Alright, so let's start with this. So if I started with a function with a constant, I need to pull out a constant, right? So equal to 2 integral t cubed dt. Alright, so they say pull down the exponent. So I have my 2, but I need to pull down 1 over the power plus 1, right? So 3 plus 1, and then we have t, also 3 plus 1, and then don't forget to add a c constant at the end, right? So let's see. So that would be 2 times 1 over 4 t to the 4th power plus the c, right? So it's like 2 over 4 plus c equal to just 1/2 t to the 4th power plus c. Is that okay? And if you, let me see. Okay. So that's the top one, 5a. Let's do number 4. So we have a power rule here, so I really should do this first. So that would be 1 over 3 plus 1, right? And then you have x, 3 plus 1, don't forget to add a c. So that would give me 1/4 x to the 4 plus c. So that would be number 4. And if you try to check it, we could if we want to. So do we want to? Okay. If we try to check number 4, we can have, let me see. Okay. We're taking d dx of 4, 1 over 4x to the 4th plus c. So we have 1/4 and then 4x cubed and then plus a 0, right? So this cancel out. All we get is x cubed, right? So it kind of like start with x cubed, supposed to end like that. So we kind of check it. Okay, so let's look at b here. So again, we should pull out the coefficient first. So pull out -3. I need to take integral of x raised to -2 dx, right? So equal to -3. I need to pull 1 over a -2 plus 1. And then we have x -2 plus 1 again. Don't forget to add a c. That happened a lot on the test. People forgot the c. So that would be a -3 times 1 over -1 x raised to -1 plus c, right? Okay, so what would that turn to be? So negative times negative become positive. This is just 1, so it's kind of like a -3 times -1 x -1 plus a c, right? So finally we have a +3, but with this x raised to -1, it go where? X raised to -1 mean x is in the denominator, so that's one of the competence exam question, right? So +3 over x plus the c. So that would be my final answer. Sorry, I have very little room here. So I hope that makes sense. Let's do one more before we stop this video. So again, if you need to pause the video so you can write down some of the information, feel free to do it. Alright, let's look at the next question, which is number 5C. Number 5C on the next page. Okay, this one, similar, we're taking an integral with a power function. So let's see. First, we are going to have 1 over whatever the power is, need to add 1, right? And then x, we have 3/2, also need to add 1. Alright, and don't forget we need to add c. That seems to get forgotten a lot. And the next part, we have 1 over, this is 3/2, basically plus 2/2, right? And then we have x also 3/2 plus 2/2. So after we clean that up, we got 1 over 5/2, and then x also 5/2, right? Oh, don't forget plus c. Let's see. Alright, so what does that mean? This means 1 divided by 5/2, right? Or 1 times 2 over 5, so it's just 2/5. So the easier way to think about this complex fraction is you just flip it. So we got 2 over 5, and then x 5 over 2 plus a c. So that would be the answer.